Hi everybody! In this section we're going to learn about cylinders and quadric surfaces. So let's remember some surfaces that we've known from the past, the first one being a sphere. And so here's our equation of a sphere. We have x minus x naught squared plus y minus y naught squared plus z minus z naught squared, which equals the radius squared. And so this is our notation. And we can tell by looking what the center of the sphere would be. It would just be this number, x naught, comma, y naught, comma, z naught. Then, if you kind of go down to 2 dimensions, the circle equation in the xy plane, just sort of get rid of this z component from your sphere equation. And then there's circles in the other planes as well, if you sort of get rid of that component. For example, if you wanted a circle in the xz plane, you could kind of erase this y component. Then a plane equation is the following. So remember how this one went. We have a times x minus x naught plus b times y minus y naught plus c times z minus z naught equal to 0. What was the a, b, and c from? Well, if you remember, that was from the unit normal vector in the direction perpendicular to your plane. So a, b, and c were the components of your vector that's perpendicular to the plane that you have. Alright, so now here's a new surface for us, and it's a cylinder. So I know it might not look like a cylinder in this format, but by definition it is. And so what a cylinder is basically this kind of like plane shape that you have this generating curve through. And then if you kind of take this line here, so you start with this generating curve, which would be this red line here, and you can envision this like a piece of paper. So you have this red line as our generating curve, and then you start drawing straight lines, so these blue lines, through the curve, but parallel, okay, to each other. So all these little blue lines are parallel to a fixed line. And then you just move that line along the curve, so you can kind of think of it like maybe one blue line that you've kind of moved all through this sheet of paper. And then when you do that, you actually form what's called a cylinder. So technically you could start with like one blue line, but then think of it as like sort of moving that blue line all the way through up here to create all these other blue lines. And so this is sort of another way to think of it. So if you think cylinders should kind of be circular like a can of soup, then if you can envision just sort of folding this paper, you kind of take this piece of paper and you kind of fold it together, you would get what you probably would consider a cylinder. But technically this is a cylinder just like this by definition. Now here's an example. Y equals x squared. In 3 dimensions, this is a cylinder. So every point of the cylinder y equals x squared has coordinates of the form x naught, and then since y is x squared, your y component, or your y point, is x naught squared, and then z values. Notice we don't have any information about z, so z can take on any values. And so we call this the cylinder, y equals x squared. And so if you want to look at it in 2 dimensions, it's just your standard parabola right here, y equals x squared. But if you tilt it sideways and get this 3-dimensional view, then you're actually going up and down in the z direction, technically all the way to infinity and negative infinity, to form this cylinder shape. And so quadric surfaces are second-degree equations in x, y, and z. So what we're talking about in this section are these types of equations that we call quadric surfaces, and what makes them is that they're second degree. So this is a second degree equation right here. Notice x to the second power. And then your variables are x, y, and z. And so your general equation of a quadric surface, and this is of second degree, and in our 3 variables, is going to be broken down into the following. Notice you have an x squared, a y squared, and a z squared part of your equation. And then you sort of kind of go downward with your powers, with your exponents. And then you have x to the first power times y to the first power. And then the combinations of the variables. So x to the first times z to the first. And then y to the first times z to the first. A, B, C, D, E, and F are just going to be coefficients. So just constant numbers. Then you go down even further and you just have your single variables, so x, y, and z parts of your equation. and then there's still got to be a constant possibly, and so we equal this to 0. So this is what it looks like, kind of a long one here, when you write it all together. So you have your three variables x, y, and z. You have the highest power on them as x squared, so second degree, or sorry, as squared. So x squared, y squared, z squared. And then you start to kind of go downward as far as powers go, and you combine. So all the variables, x with y, x with z, y with z, and then your individual terms with x, y, and z alone, and then your constant over here. Now, not every equation will have all of these terms, and that's what we're going to get into with our different shapes. So maybe you'll have just an x squared plus a y squared, and maybe nothing else over here. Or maybe you'll have a y squared and an xy, and then maybe a j over here. So not all of these terms will show up in every equation. Here are your quadric surfaces. So these are the shapes that we're going to talk about briefly in this section. So notice these are three-dimensional shapes, and we have equations that describe each one of them. So let's start with the ellipsoid. So what I want you to do is be familiar with the equation and what shape it represents, and you'll start to see some patterns and sort of how to come up with this. So an ellipsoid, if you kind of think of it sort of like the equation of a sphere, it was x squared plus y squared plus z squared, but we just divided by whatever number we needed to over here to make this a 1. And so that's an ellipsoid. So it's sort of like a sphere, if that helps you remember, but not technically round in every direction equally. So like maybe a ball that kind of got flattened in one or two directions. And so if you break down the ellipsoid, it's actually made of three ellipses. So an ellipse in the xy plane, an ellipse in the xz plane, and then an ellipse in the yz plane. And you kind of put all these together to form what's called an ellipsoid. So let's take a look at an example for this one. So identify the surface defined by this equation. So what I want to do is I want to figure out what surface is this actually looking like. And I'm going to just tell you right now it's an ellipsoid because that's all we've mentioned. But basically I'm going to give you the other equations for the other surfaces, and you sort of break the equation down to make it look like one of those equations. So the first thing we're actually going to do is we're going to use completing the square. And so all I did here is I took my x terms and I moved them together. Same thing with y's and same thing with z's. And then I moved this 1 to the other side of the equal sign. So with completing the square, we have to find the missing piece and we need to add it. So for the x's, that's going to be half of this coefficient -2 and squared. So that becomes 1. So we're going to add a 1 to both sides of our equal sign. For the y terms, that's going to be half of this coefficient 4 squared. So that's going to be a 4 that we're going to add to both sides. And z, there's no other z terms. There's no linear z terms, like z to the first power. So we don't have to do anything there. And so we end up with this version of our equation. And now we added those missing terms so that these trinomials in terms of x and y are perfect squares that we can factor. And so this becomes x minus 1 squared plus y plus 2 squared, and then still our plus 4z squared. And then the right side of the equation just equaled 4. So now we're almost to a format that looks like our ellipsoid equation. So technically you didn't know that it was an ellipsoid, I mentioned it to you, but we're getting to where it looks like the ellipsoid equation. And so if we just divide by 4, notice what we end up with. This looks very close to our ellipsoid equation, just with numbers. And so here's our equation, and then this is the ellipsoid equation. And so we're just not centered at 0, 0, 0. That's what this one would be, this in general one. So this one is centered elsewhere. So this is an ellipsoid centered at +1. So it's always the number after the minus sign up here for the center. So +1. This would technically be minus a -2. So -2. And because you don't see any numbers with z, you would say 0. So this is the center of the ellipsoid. And then here's what it would look like if you start to draw it. You would have 3 ellipses in the different planes. So you have an ellipse in the x, let's go xy down here first. In the xy plane, when z is 0, that would be this green one right here. The ellipse in the xz plane would be this red one. and then the ellipse in the YZ plane would be the blue one. And so if you put this all together, it actually looks like this. And so if you remember when you learned about ellipses for the first time, when you learned about conic sections, basically from the denominator you can tell how to move left and right from the center. So let me just briefly talk about that. If your denominator here is 4 under the x term, if you look back up here, you want that the square root of that number. So this is really 2 squared. That's just letting you know that from the center point, you're going to move 2 away from it, left and right in the x direction. Sorry, yeah, so on the x-axis. So 2, we'll say forward and 2 backward on the x-axis. Same thing for y, because this number under the y term is 2 squared. So in the y direction, you're going to move from the center 2 forward and 2 backward. And then underneath z was a 1 squared. So from the center, you're going to go up 1 and down 1. And that's one way to draw it. So let me show this to you with a 3-dimensional graphing tool. So I'm just using a website, GeoGebra 3D. And here's our equation that we just looked at, then our ellipsoid shape, and I have the center mentioned right here. And so this way I'm able to kind of show you the 3-dimensional side of it. And if I sort of just look at the individual planes, notice, let's start actually in the XY plane. So let me try to get my orientation like we normally do, positive x to the right, positive y up. And so it looks like a circle actually in the XY plane, because the denominators on x and y were the same number. They were both 2 squared. So it actually looks like a circle, but technically that's still an ellipse. And notice from the center, for the x, you go 2 to the right to get to the edge and 2 to the left. Same thing from the center for y, you go up 2 and down 2. Now if I rotate it back to z, this is a view for the YZ plane. Kind of try to get it straight, there we go. And notice from the center, you go up 1 and down 1 to get the edges of the shape. So this is an ellipsoid. Okay, so we're going to talk about a handful more of the quadric surfaces. I'll give you the name and the shape and then the general equation. So this one is the hyperbolic paraboloid, and so it kind of looks like a saddle over here. You can visualize that in 3D. And here's the equation, y squared over a number minus x squared over a number equals z, and so over some number. And so what you can do to be able to sort of identify that this is the shape is sort of break down the equation by ignoring parts of it. Here's what I mean. Let's say we ignore the x's right here, the term with x in it. Then what you really have is y squared equals z, which that's just the equation of a parabola. Happens to be this blue one right here. So y squared equals z is a parabola in the yz plane. Then if we ignore the y term over here, we have that negative x squared equals z. So z equals negative x squared is a downward parabola, this green one, in the xz plane. Okay, and so then there's 2 more shapes we actually have going on in this hyperbolic paraboloid. We have 2 hyperbolas. So if we have y squared minus x squared when z equals a positive number, that's going to be this red hyperbola. Here's half of it facing this way and then the other half sort of facing backwards. And then if you said something like y squared minus x squared equals a negative z value, we would have something like this equation, or you can sort of switch it and say negative x squared and then, positive x squared minus y squared. And that would be this yellow parabola opening like toward us and then back away back there. So this hyperbolic paraboloid is actually made up of parabolas and hyperbolas, and that's how we get that shape. So just so you're aware, in general, this is just one version of this equation, but you can change around the variables and still get this overall shape. So what I'm saying is you can say something like x squared minus z squared equals y. It's still a hyperbolic paraboloid. It's just going to be oriented differently. So opening in a different direction and sort of shifted, or you can almost think of it like rotated at a different axes. This one has like this like I mentioned, it looks like a saddle, so you would imagine like a horse maybe on the y-axis here. So just a different orientation if you switch around the variables. Maybe the opening where the horse would be like on the x-axis or even on the z-axis. Here is the elliptical paraboloid, and its equation is x squared plus y squared over some number squared equals z over a number. So one way to think of it is like x squared plus y squared would represent an ellipse, right? So it's an ellipse in the xy plane, okay? And it's an ellipse. It could be a circle if a and b were the same numbers, but technically we just say it's an ellipse in the yz plane because of the x squared plus y squared. And then it equals something with z, so it does have this z component. So this one's sort of like a bowl shape. Okay, so that's our equation for our elliptical paraboloid. And again, you can change these variables around. This could be like maybe z squared plus x squared equals something with y. It would still be an elliptical paraboloid, but just opening instead of up in a different direction. And then if it helps you also, notice that you can break this apart. You can say z equals x squared, and that's a parabola in the xz plane, this purple one. And you could say z equals y squared, and that's this parabola in the yz plane, the blue one. The next one is an elliptical cone. So the equation here, x squared over a number squared plus y squared over a number equals z squared over a number. So for this one, you have your x squared plus y squared, which would form an ellipse in the xy plane, which is here, this blue ellipse. But then also down here, this blue ellipse. Okay, and then you have your z squared component. So with this one, if you kind of separate it, you can think of it like x squared equals z squared, and if you square root them, you'll get these lines. Same thing if you separate y squared equals z squared. That's how you would end up getting these lines as well. So that's an elliptical cone, so it has this top half and this bottom half down there. The next one is our hyperboloid of one sheet. So that looks like x squared over a number plus y squared over a number minus z squared over a number, and we set it equal to 1. So with this one, if we start to break it apart, you can say the x squared plus the y squared, that would form these ellipses in what's parallel to the xy plane. And then if you sort of kind of separate some terms here, so let's just ignore y for a moment, x squared minus z squared, well, that would actually give us a hyperbola in the xz plane. So that's this purple line curve kind of in the back, as well as this one in the front here. And then very similarly, if we ignore the x's, we can say y squared minus z squared, and that's actually a hyperbola in the yz plane. So that's this purple curve kind of going left and also going right. And if we kind of put that all together, we end up with this shape, which we call a hyperboloid of one sheet. We also have a hyperboloid of two sheets. So notice the difference on the equation. This time it's z squared and then minus x squared minus y squared. So on the hyperboloid of one sheet, it was positive x squared plus positive y squared and then minus z squared. So in this one, we're kind of subtracting from z. But once again, you can always switch around your letters, and it basically changes the orientation of your shape. So instead of it opening up and down like this, it might open left and right or back and front. So if we break this one apart, notice what you have. If you kind of factor out this negative sign right here, you can say that you have an x squared plus a y squared. And so that would be your ellipse that's in the planes parallel to the xy axis. And then if you say, okay, just z squared minus x squared, well, there's the hyperbola, the blue here. Right here, the pieces of the hyperbola in the xz plane. And then the last part would be if you say z squared minus the y squared. Well, that's also a hyperbola, but the purple ones. So hyperbola in the yz plane, going up and down like this. So if you draw that all together, you end up getting like these two bowls facing in opposite directions. So what I want to finish with in this section is basically to just show you some examples. So based on the equation you're given, you can identify the surface relatively quickly. And now, if you have your equations of your quadric surfaces available, it'll be faster to be able to kind of line up what you're given with what you know. So for this first example, x squared plus y squared plus 25z squared equals 9. If you look at your options for your quadric surfaces, they pretty much all equaled either 1 or something with maybe like a variable like z in it. And so what I want to do is if I just take a moment and I divide this equation by 9, think about what you'll have. You'll have x squared over 9 plus y squared over 9 plus 25 over 9 z squared equals 1. And so the idea is to sort of break this apart into maybe two variables at a time. So you would have an x squared plus a y squared, which that would be an ellipse in the xy plane. If I divide by 9, both denominators on x and y would be the same. So it pretty much looks like a circle in the xy plane. And so I can look at my options here so far, and they all kind of have a circle going on in the xy plane, or parallel to the xy plane. So far that doesn't quite tell me enough. But then I have this plus 25 over 9z squared. And so my denominator on, or my, you say coefficient on z squared is different than x and y. And so in that case, that means that it's not going to quite be symmetrical about z. And so that would be, and then also the fact that it's being added, that would have to be options B or C here. C is symmetrical. It's a sphere. Everything looks the same in all directions as far as how far out, up, left, and right I go. So the real option here, the only real option is B, that this is an ellipsoid. So this is an equation of an ellipsoid where x and y have the same denominator, so it's symmetric, kind of going around in the xy plane. But my z denominator, if you want to put the 25/5 out as the coefficient, you're going to be moving a little differently in the z direction. So that's got to be the one. Alright, let's try another one. 9y squared plus z squared equals 4. So notice there's no x's here. So that means for us that x can take on any value. And if you sort of look at all three options here, x is doing that. You have some shape in the yz plane, and then x is, all the x values are being assumed. So it's kind of the forward and backward of all these shapes, like toward us and away from us. So now if you think about it, y squared plus z squared is an ellipse in the yz plane. And so you can divide out the 4, but you can tell pretty quickly just by knowing that that's an ellipse, the y squared plus z squared in the yz plane. So it's got to be option C here, but let's just verify. If we divide by 4, we're going to have a 9/4 for y squared, and then we're going to have a 4 on the bottom of z squared. And so it's going to actually grow more in the z direction, because if we consider our denominator here, you'd have to actually say technically 1 over 9/4. That's going to grow a little less in the y direction. So basically, it's going to go a little higher and lower in the z than it does in the y direction. So it's got to be this option. Okay, let's try another one. So we have 6x squared plus 4z squared equals 280. Now this was pretty similar to the last one. This is going to be an ellipse in the xz plane just by seeing the fact that it's x squared plus z squared and no other variable. So y is not mentioned, so that means y cannot take on any values. And so you have this elliptical type shape in the xz plane, and the only real option here is A, because if you can imagine this, like, take a look at this endpoint here that's circled in black. That's an elliptical type shape, and then because there's no y mentioned, it basically is this ellipse extended in the left and right of all the y values in space. So it's got to be that one. And there we go. Alright, so this wants us to identify the surface, and so our choices are cylinder, paraboloid, ellipsoid, or hyperboloid. Okay, so what do you think? Cylinder? Let's see. Yeah, good. Let's try one more. Okay, so take a look at this one. 19x equals z squared minus y squared Alright, so this one has a minus sign. So if we look at all of our options for our quadric surfaces, what does this look most similar to? And I mentioned when we were talking about them, the variables can kind of switch places. So nothing that we actually went over with the general equation had this exact form, where it was z squared minus y squared equals x. But if you recall what we talked about, this is the same as the hyperbolic paraboloid, okay? Because if we just say that it's a variable squared minus another variable squared, and then equals our third variable, that was our hyperbolic paraboloid equation. And so out of our three choices, only one of them is a hyperbolic paraboloid. It's got to be C. But imagine if all three of these were hyperbolic paraboloids. You'd have to know which way this is oriented. So you have z squared minus y squared. And so your hyperbola shapes are basically going to be, if you slice your coordinate system at x values. So z squared minus y squared equals some x value. So I'll sort of try to mention it here. Imagine, if you can, sort of taking a slice out of this shape toward the back half of it. Notice you have this hyperbola, edge of one half of your hyperbola here. And you can't see it here, but it'd be this other half in the back. And that's going to be at a certain x value back there. And then same thing if I take a slice out of this shape here at a positive x value, the resulting shape would be a hyperbola. But then let's work on the parabolas. You have x equals z squared. So x equals z squared is going to be a parabola in the xz plane. So does that make sense? Let's see. It's sort of this front part here. So this black curve right here, that is a parabola in the xz plane. And then x equals negative y squared. So that's a parabola in the xy plane. And that's kind of this little back piece right here. If you can imagine this little line that I'm pointing to right here in the middle, and it's a parabola shape. You can't see the other half of it, but it goes sort of like this piece here. So that is just some examples for how you can kind of quickly identify which surface you're working with based on your equation. Thanks for watching.